I will start now. First thing I'll say is thank you all for braving a 9 a.m. slot, which said advanced after a party. I know for a fact that when I first saw that was the time slot I had, I decided to try and put more pictures in. So this is going to be a talk which is more about the theory and not so much code, because to be honest, I struggle to read code on screens at the best of time. And it's 9 a.m. and there was a nice party last night, it's a little much to ask you to start following through a ton of Java, Scala if you're feeling brave, Haskell if you're feeling strange, or Rust if you're feeling modern. But no, not today. So, without further ado, welcome to my talk about a record's acid trip through Kafka. Everything has to have a pun at some point, so the warning is very apropos. There may be puns, most of them will be intentional. I will claim they're all intentional. You may realize some of them are not, particularly if I start giggling along as well. So, a little bit first is, who am I? So, hi, my name is Ben Gamble. These days, I kind of work as a bit of a tech sommelier. My job is mostly to kind of pair the various technologies you need, from your Kafka over here, your database over there, maybe some cheese to go with it. And I work at a company called Ivan, who are a managed hosting provider to kind of give you all the data tools you need in various clouds. And my role there is more about trying to show the big picture, see what you can really do, and help people understand the possibilities with the open source software. In the past 15 years, I've spent my time working on nearly everything you can imagine, from literal MMO games with people like CCP, on EVE Online, and a fair number of others I'm not allowed to talk about, to things like medical device development, augmented reality applications. I even built a Google Glass company. You can see I try things which are fun. I am mostly blind, the stick is for that. I have severe tunnel vision, so if I appear to be scanning around and looking at you, I might be. It's not always guaranteed. I will be asking for shows of hands every now and again, and then scanning wildly to see roughly what's going on. I do code in Rust for crustacean jokes because of the Ivan logo is a crab. I have decorporated all these slides because at one point there was a corporate deck. So I do apologize if the style shifts here and there. It's mostly that when you try and remove styling from slides en masse, it does things, and things can only be described as the principle of most surprise, particularly with slideshows. So what is this talk about? This talk is really about design patterns and the ones you end up doing because of kind of absolute pragmatic approaches. We all try to design things with best practice in place. We love the idea of starting with a system with a clean sheet and saying we can apply everything we know, build a clean system. But through bitter experience, we all know that you're never the first one on the scene. You're also not the one who owns everything. From the fact that we have to deal with third-party APIs for often 3/4 of the execution of what actually happens in our project, to the fact we have to deal with the fact that the code base might have been there for 30 years. Even worse, you might have written it some years ago. And there's nothing worse than seeing your own code and going, oh gosh, what did I do? And having to deal with a pragmatic nature that this code is in action, it's doing things. It has the one true curse of legacy code, which is what legacy code really means is code that makes too much money to be deleted. And that is a really important fact, is legacy code is making too much money to be deleted. And if it is that, the practicality problem simply kicks in of you can't get rid of it easily. And most importantly, this is my current thinking. The best thing we can do in software, particularly when you get beyond the kind of mid-level, is you're there to learn, you're there to teach, right? And this is my current thinking, as I said, informed mostly by experience, informed also by a lot of reading and other things. I will link to two of the most inspirational talks for this talk at the end. But this is, as I said, a snapshot in time of where I'm at. And also, this invalidates a lot of what people consider to be great practice. But through the whole kind of lens of practicality and some of the examples I hope to give, you'll kind of see where I'm coming from. And this is also a kind of a core principle. Hands up who's seen this picture before. Hands up who's heard the quote before, which is, those who cannot remember the past are condemned to repeat it. Hands up? Cool. So this is quite a famous painting. It's in the Smithsonian. It's basically about enshrining the idea of we just keep recreating the same things, but different. And the but different bit is the important thing. There are loads of interesting patterns as you go back in time through software engineering, and they were all built to deal with a set of realities as they were. What is fascinating is, as you start looking at the patterns going backwards and forwards, is they haven't really changed that much. Sometimes we've got faster, sometimes we've got slower. Sometimes the compute is right at the edge, sometimes it's right in the thing. My current favorite thing is that most serverless technologies are basically just timeshares for the 21st century, as you're literally just borrowing a time slice on someone else's huge machine somewhere else. And the kind of analogy holds remarkably true the more you look at how a mainframe works versus how Firecracker works. It gets insane when you see the kind of parallels. So with that in mind, let's remember the monolith and those lovely apps we used to build. A single structure, carved from stone, everything you did was inside it. One big application and a nice relational database behind the scenes. And these were beautiful. They were quite simple to make. Hands up here who started building monolithic apps on relational databases. I'm going to guess that's well over 90% of the room, and that feels about right. And, it kind of was enshrined with those early days of things like the LAMP stack, Rails if you're feeling brave, Django and Python if you wanted to be one of the hip kids, and Node.js if you wanted that lovely asynchronous vibe. But because we're a DevOps, and I want to bash everyone equally, we're going to bash a bit of Apache struts. Hands up here who suffered Apache struts. I am so sorry. And Tomcat for those who just had to, and it's still there, and I don't know why. But these were kind of the early days of kind of like when the web started to pick up. Everything we did became a back-end service for something, and increasingly work had to be done on someone else's, or not on the machine it was originally on. And distributed systems became the norm because this is the big problem: is as soon as you have a browser and then a server, that's a distributed system. So already we're starting to enshrine a lot of the things we always try to avoid. And the real problem with these things is they are held to scale. And they're held to scale in many ways. And this is not just the idea of can we put more cores on the machine, because that held true for a shocking period of time. You can ramp machines vertically to a rather terrifying degree. I think there's still a website somewhere that says, will it fit in memory? And it just checks if you can put enough RAM in a machine to solve your whole problem with never leaving that one machine and never leaving the RAM. And what really came across in scale, though, is not just things like Amdahl's law, but Conway's law, which is how do I get more people to operate on a problem? How do I separate out domain spaces so that I don't have to have all the expertise in one place? Because microservices and what their ilk came from was not just the idea of, I want to put more machines on a grid to put more code behind it and put more processing behind it, but instead the idea that I need to have domain expertise. I need to separate out thinking and workers more than I need to separate out runtimes. And that's actually an important point to kind of get to, which is microservices are always going to be slower than a monolith if the monolith is on one machine. The network isn't free. Hands up who here has had to suffer this thing of people adding Redis caches to things because they think it'll make their code faster for no reason. Yes, I can see the bitter nods. I now know I'm in the right place. And each service behind an API became this enshrined thing. You might have the email service, the user auth service, the fraud service, whatever else. And because it's DevOps, let's make it Spring. Yes, I am, as you may have guessed, not always been a Java engineer. I did build a lot of Android apps back in the day, but I found that over time, the patterns hold true, and Java's the best place to enshrine patterns because there's the most angry developers in it. Not the most developers, the most angry ones. What that says about us, I'll leave up to you. I mostly think it's because we care, or I like to think it is at least. So that's kind of how we dealt with the kind of separation of concerns, but how is data managed? So let's start with what kind of a couple of these services. So what you got was, you start with, let's say, users, and we went for Postgres. But the problem ends up being is once you have a good tool, you tend to reach for it again for the payments and for the shipping. Hey, even for the yoga service maybe. And you get this point where everything starts to become this idea of data just lives in the big relational database at the bottom. And suddenly you realize that the monolith didn't really go away. It moved. And you end up with something like this. And you think, why can't we just scale it up? And the answer is, yeah, you pretty much can. Postgres goes a long way. With tools like Citus, it goes even further. Foreign data wrappers allows you to shard. But eventually you get to this point where it's starting to exceed what makes sense. And particularly when you're dealing with services with data moving around in them, you get something a bit like this. And it looks great until it isn't. And this is that horrible fact of even MySQL, its ability to kind of throw millions more connections onto it, you still end up with this continuous problem of you have transaction blocking transaction blocking transaction blocking transaction. And fundamentally, you will hit a point in scale where these systems were just never designed for that. But let's talk about why this matters, because That sounds like a fun abstract problem, but I'm not here to throw Greek symbols at you. I'm here to talk about like the actual practical side of things. And the real kind of absolute problem here is users hate waiting, right? And this is not just human users. There's nothing worse than when you're on a beat, you're selling a service to someone and they can hammer your API at arbitrary speeds, and you now have to handle that flow of traffic. And their API hates waiting, and their users hate waiting too. And when you're 4 APIs deep down the chain, suddenly you have no idea where the thundering herd's coming from. And you know for a fact that if you don't meet your n milliseconds, n seconds SLA, no one's going to be very happy with you. So you start with something simple, and you think, I'll scale out some applications. And then we enter the cache. This is back to kind of just like the thinking of how do you make things a little better, right? And I'm going to keep saying Redis for the sake of today, because Valkey is not embedded in my mind space. Similar to how I'll probably say Elasticsearch and still use the OpenSearch logos, because that is what I remember it as, and programmers change much slower than licenses do, as it turns out. So, you add a cache. It improves performance because suddenly your database isn't bottlenecking you so much. But then you go about finding things, and yes, as I mentioned, OpenSearch. I'll remember it today. And you have this kind of idea of saying, more features, more technology, more things. But this only really solves that edge piece. And when you start dealing with more of your own stuff, right, you have services, and they've got to start talking. And, logical first thing is we've got a REST service here, because REST is nearly always where your edge is, because everything speaks REST, for good or bad. And suddenly you think, why don't I use more REST APIs inside my system? Hands up who's got microservices on REST APIs? A few of you all. And who's had to put caches inside your own firewall to handle those REST APIs on your microservices? Because suddenly, yeah, a few of you as well. And this is the kind of one of those interesting problems where as soon as you start having these like truly synchronous, truly connected APIs, which are all CRUD behind the scenes, fundamentally you've got the same problem your edge now has, which now means you have various caches expiring at various points inside your network, and you've added how much more technology to make it work. So a question I'm going to ask a few times is, have we been here before? And I'm going to say a resounding yes. Now, who here was part of the ESB wave and had to put these things in across their various networks? And, these are wonderful tools. MuleSoft is this lovely idea of exposing all your APIs inside your network. ActiveMQ, I have suffered personally and had great pleasure ripping out of people's systems over the last couple of years. Rabbit, I have bad things to say about as well. But all of these things were basically still part of the same problem, which is I need to loosely couple various systems across various points in time. But what ends up happening is you end up with a bit of a distributed monolith, because you had a bunch of systems reliant on these relatively transient queues, which are just connected kind of loosely between things, and you couldn't really take systems out without breaking things. And let's try again, but with feeling, or in this case, durability. And this is where kind of Kafka comes in, at least for me. Now, Kafka, hands up who's familiar with Apache Kafka, right? So a lot of what I'm going to talk about now assumes at least a passing familiarity with Apache Kafka. Now, Apache Kafka took that kind of approach of the middleware, where everything was this kind of pre-processing, processing, post-processing, JMS queue type structure, where you'd expect the queue to do some intelligent work, and said, let's actually just simplify it and say we're going to gather the data, store it durably on a disk, and then just give the ability to distribute it in a much simpler pattern. Kafka's kind of like true kind of genius was, if we make the pattern simpler and make it more durable and more kind of higher throughput, we can do a lot of things and get away with things you wouldn't have thought possible, because we're not trying to put intelligence into the middleware. Now, what that really gives you in the terms of durability is durability equals decoupled. And the durability here is we have near unlimited back pressure. We can put terabytes of data into Kafka. So you can just spool at it gigabytes per second. You shut off the reader. You wait 6 hours, 5 days, turn it back on. It will continue where it left off. And it means that you now have a service which is durable to the individual points of failure. And durable to this doesn't just mean that you can turn things on and off and it'll keep going. I mean, you're durable to the fact that you have your massive thundering herd of data, which you can now read at a speed you want. And because it can treat a stream as a batch as a stream as a stream, and a batch as a batch, yes, that was well practiced, you can do all this stuff without worrying. You can suddenly go, I know I have 5 days of backlog, just batch fetch huge records out. And this isn't a problem with Kafka. And one thing, I couldn't remove all the corporate logos off, was this. So you end up with this idea of building on the middleware, where you have like a kind of data plane between things. This is your service mesh, if you're that way inclined. I try to stay away from some of these things because they all have subtly different meanings, and I forget between conversations which they are. So it's just a plane of data on Kafka. And this is kind of like bridging between services with different kind of guarantees. But let's talk about guaranteeing things. And this is where we get to ACID trips. But we're really talking about ACID transactions. So hands up here who's familiar with ACID transactions. I like that that's 90% of people. So this is kind of from 1983, from Anders Reuter and Theo Harder, who basically encoded a series of behaviors which basically enshrined what they considered to be the important things when doing work which was important. So things like atomicity, and which basically says the whole thing works or nothing works. The idea of durability, it better be written somewhere. Though durability is a very questionable concept, I find, as what is durable in the cloud is an interesting experience of, is a network attached store in the cloud really durable? Because if you turn it off and on, it's all gone. So is S3 durable? As far as I can tell, yes. But I'm going to hold to as far as I can tell yes, because I've yet to be proven wrong. But I was proven wrong about every other layer of the cloud being durable so far. So, actually no. Then the Google thing happened 2 days ago. So I will even say that object storage might not really be durable, because Google might just turn off your whole account for you. So, you never know anymore. The kind of isolation and consistency pieces are also important, because the idea of saying you must kind of maintain this. But what gets really interesting is when you look at what's under the hood of all these ACID transactions, is there are various kind of ways you enshrine this inside your database, which are a hell of a lot more complicated than you think. I'm going to come back to that because it comes relevant. So we need transactions. Now, this is going to be this is an actual example from one of my clients right now. And yes, it's in Node. And I'm leaving the Node things on there rather than changing it, because Node adds additional interesting complexities and not necessarily what you think. So what they have is a payment system. Now, the REST API here calls out to an external part of the external payment systems, and the batches they push off go to other workers which actually action this, right? But the business worker, so there's the API edge, there's a business worker that does all the kind of internal verification checks, confirms things are real, and then they have that REST API which calls external services to manage payments, and they have a database at the bottom which kind of just makes sure that certain things are happening. And they're kind of wondering why things were failing and where things were going. So to start with, there were problems like they didn't have rate limits. And the first thing you need to do if you're going to try and respect a transaction thing is have some rate limits. In distributed systems, there are a couple of absolutely enshrined things I have learned the very hard way. And rate limits is probably top of the list, which is if you don't have a way to have a max in-flight requests at any given point in your system. You happen to be right in front of me, so if I look at you a lot, it's just physically where you are. It's the idea that you have to have these things at every layer. And particularly as you start seeing these things, you get this kind of continuous problem. Now, dead letter queues are an interesting kind of feature of distributed systems development. Hands up who has built queue systems with lots of dead letter queues in them. Quite a few. Hands up who actually uses dead letter queues as a reprocess technique. Hands up who's had that fail miserably on them and had to deal with it differently. That's actually slightly more. So a kind of a bitter experience of mine has been that if a record has failed on retry, on average, it cannot be salvaged. Hence, log it to something useful. Send it somewhere where you can analyze it offline, because particularly for anything as important as a payment, or in a previous company I used to run, shipping stuff, like I have a package in flight and the record for it is damaged. That needs to be fixed, nearly always by a person, because you cannot easily recover it, even if you go back to the source. And famously, when I was dealing with packages from UPS, some of them had dimension fields as mass. Some of them had dimensions fields as height, width, depth. And there was no way to tell as they came in which was which. And initially, it was simply we wrote more business logic for it. But as we found out with formatting changes and fun systems that involved physical AS400s, you couldn't even guarantee that. And what ends up being is that you have records that are completely unrecoverable. So if you have a problem, log it and move on. And this is the thing everyone says about Kafka is, I can't knack and then go and I have a head of line blocking. And the answer is no, just acknowledge it and move on. Then just publish it somewhere else. You do not need to actually act on a package in Kafka. So let's get back to wrapping things in transactions. So the obvious one is here. And this was the first one the kind of client noticed. And they said, yeah, let's just use Postgres as our kind of transaction across the whole thing. And that didn't work great. But Kafka does have transactions from KIP 98, which is quite literally very early on, as we're on KIP 900-ish now. So this Kafka improvement proposal. Exactly once delivery and transactional messaging has been in Kafka for a very long time. It's not exactly what you think, and this is one of the only two pieces of code you'll see, which is for the Kafka producer, you create something, you give it a transaction ID, which matters. So this basically means this producer creates transactions with this ID. And then you make sure you init the transaction stuff on it. In other languages, this gets a little bit different, but fundamentally on this side, producer-wise, it's actually quite simple. What happens in Kafka is now you have transactions across every single publish. But what happens is, as you publish to Kafka and you finish your transaction, if you do not complete the transaction or you fail a transaction, the messages don't actually leave Kafka, but they're flagged as an incomplete transaction. So you can, at the other end, and this is the important point, you have to tell it to have isolation and only read committed things. So this is the big gotcha in Kafka, which is your transactions matter as long as you tell Kafka they matter. If you don't tell Kafka they matter, Kafka doesn't care. And Kafka is one of those pieces of software which I find to be infinitely powerful, yet has some of the craziest defaults you will ever come across, because it is old and it came from a different place. It came from logging data. It came from click streams where losing the odd click didn't matter. They made it super reliable and super safe, but the enshrined old behaviors are still there. So what you end up having to do is make sure the defaults are correct. So a fun one in the Node.js example, and really I'm highlighting this particularly here, is in the Node.js example is you have to basically turn down the number of in-flight max requests to 1 to have any sort of durability guarantees or any sort of actual transactional guarantees, because it's a Node.js server. Node has this wonderful asynchronous property where it'll just keep going, which is wonderful until you realize you're trying to do things transactionally, at which point it sucks and you can't stop that. So we actually get to the most complicated piece. And now we've got transactions in Kafka in 2 directions, and we have this wonderful Postgres thing. So doesn't this look a bit like two-phase commit? And that's bad. Hands up here who's had to fight two-phase commit. Hands up here who would be happy to fight two-phase commit. That is the right answer of nobody. Yes, two-phase commit sucks. And so let's talk about a failure, because of everything we build is kind of determined by what its failure mode is. At least when you get to a certain point, resiliency matters more than anything else. Most CTOs say their job is uptime for a real distinct reason, which is they're next on the line when it all blows up. So you consume from Kafka. And the best thing about consuming from Kafka is if you turn off the default auto-commit offsets, by default, if your thing crashes, you'll reset to the same record again. So that gives you a transactional consume, assuming you have isolation on. So now you have a transaction in PG, and then you try and produce transactionally while the PG transaction is live, and you close one. And if you fail anywhere before that orange line, you're in a good place. You can restart that node, it'll come back up, it'll do exactly what you expect. But what happens if it fails at the blue line? Because the problem is now we have the full two-phase commit problem of who is the transactional owner, right? And they have to be able to rewind. So let's say you fail after that. So we've produced, but we haven't committed an offset. And we ended up with this absolute terrible hack in this real circumstance, which was literally doing a Kafka get through the REST API of Kafka to confirm where the offset really was and do this weird comparison. It was genuinely terrible. The worst thing is it worked. And as one of the things I can safely say from bitter experience is when something works and there's a payment system which is currently live, it will go live, it will stay live, and it might never be taken down. And it will haunt you. It really will haunt you. So there are approaches here. So hands up who's familiar with the outbox pattern. I see a few hands. So I'm going to explain in detail. Let's start with some services. We have, order service, payment service, customer service. Now, e-commerce is kind of the example of most things because literally everything turns into an e-commerce at some point. We're all selling something online, whether it's our API, whether it's goods, whether it's something else. Even when we're a bank, we're still dealing with commerce-y type stuff. And first thing you end up doing is adding some sort of state to everything. Who loves the idea of stateless services? Who has got a stateless service? Oh, wow, a hand. That's like unexpected. Generally, the problem is that state is valuable. State's where all the value lives. So what happens then is, as you build out these things, you can actually take advantage of the fact we have a series of different ACID verification layers along the way. And we can effectively say, send a request in. It's now in orders. From orders, we can capture it using Debezium. There was a great talk on Kafka Connect a few days on Wednesday yesterday, which if you haven't seen, I recommend going seeing. It was here, and there's a fair number by a guy called Gunnar Morling as well, who helped create Debezium. And Debezium is a way to do change data capture. This is reading off the transactional logs of relational databases and equivalents, and then being able to emit these events with exactly one semantics if you choose a recent version, which basically means you now have transaction in, transaction on, and you can go through the system and send the data into the customer service, do the work, Debezium it back, then go through payments, Debezium it back. And you can start to see that you can build up these transactional chains where you're never really dealing with a horrible commit boundary. The extra advantage here is when you take that first message in from the user and commit it to a database, that user now has a place they can now check the status of what's going on. And if you've ever served a REST API as a SaaS product, the number of people hammering it for status never goes down. Even if you just hold that connection open while your system completes, people still want something they can hammer for the status. I don't know why. I think it's psychology. And then what happens here is now we have a system where we've basically started using the fact we have relational stores along the way to kind of give us a few more ACID boundaries. And we get this kind of a bit better scenario, because if you fail at any point here, we're already on a transactional boundary, right? We've already closed all the transactions, because if we fail anywhere inside the Kafka consume, it doesn't matter. If PG is not committed, it doesn't matter. It's PG. You just say, I'm writing this record to PG. PG goes, I've got it. It doesn't matter. And you can check that immediately. If you're actually reading in Debezium fails, it has offsets. It will know where it started from, and it'll keep going. But let's start with, how can we guarantee everything? And we're going to come back to the same problem again because of users hating waiting. And I'm going to kind of use this bit now to dive into the other half of the example, which is, let's actually take a few specific pieces, right? So you're on your phone as a user, right? And you want a recommended movie, action adventure, subject 5-year-old, lots of animals. I have kids. This is a serious thing. I want to make sure I get a recommendation that makes sense for me in the situation I'm in. You want to make a trade. I've used GameStop and Bitcoin for meme purposes, but in general, like, if you look at how post-trade reconciliation works, it's a very complicated multi-step process. And what happens here is, you have to have the right thing. I have to have the right thing. If you're actually at an institution, that might mean you have to trade between your internal desks to get the product you've actually promised someone, particularly in energy trading. And this gets rather complicated because to fulfill the trade is a multi-step process. And I've used many taxi booking apps, like I did this morning, to get here. And, when you're trying to book a taxi which requires a certain capacity, let's say there's 5 of you or 7 of you, or you've got a ton of luggage, or the dragon going to Narnia. And these things get complicated because you have a series of annoying criteria to meet. And this is the real kicker, is the window success. If you don't recommend a movie to someone after they've left a session within about a second, you're not going to succeed. With a trade, it is user-defined because nearly always there's like fill or kill orders, or there's the fact that you must complete within certain time windows. It is defined by you or the system. And with a taxi, if I wait more than about 5-10 minutes, I'm in a bad way. And let's look at the consequences. If I churn a session in a movie, it's bad. Like, you leave Netflix, but you didn't find what you wanted. You leave iPlay, didn't recommend the next thing. Or the kids watch the 5-minute episode of Bluey or 2-minute episode of Hey Dougie, and they can't find what they want next. They're going to come to me and start bugging me. And if you're cooking, that sucks. And with trades, there can be near unlimited penalties for making a mistake. You have to complete everything or nothing. So you must make no action or everything, and it must be correct. And with a taxi app, I know for a fact that if Uber fails me 3 times in a row, I'm moving to Lyft until Lyft fails me 3 times in a row, then moving back or around the circle. So you like churn some for a while. So then the question is, how do you manage these things behind the scenes at scale and have enough asynchronicity that you don't have to wait for bits to complete? So there's a kind of a great talk about completion criteria, but let's talk about, remembering things we've done before. And let's think of this as Saga patterns on the stream. Because hands up who's used Saga patterns before? Hands up who's read the book they came from? Yep, a few people, maybe one person. So Saga patterns are one of those like enshrined design patterns from the 90s that kind of keep coming around perennially. And what this says is I have a series of statements which I need to do to complete an action. And I have this list that needs to be completed. And when you're doing it on a stream, what you can do is you say, I just need to join these pieces together. And when I have a complete piece of data, I know the thing is complete. So let's say it's that trade reconciliation. I have to get I have to get the oil desk to agree, the wind desk to agree, the power desk to agree. And once I've got all those people to agree, all their streams come back in, the join fires, I have completed the action. Perfect. I now have a way to basically know when this is happening. So, reason we join on a stream is we can be fully asynchronous. A lot of these actions previously was almost, we swallowed the bird to catch the spider, we swallowed the spider to catch the fly. If you don't know why we swallowed the fly, perhaps we'll die. And the problem ends up there is, if you're waiting for all these things in order, like one of those JavaScript pages loading without promises, you have no idea how long you're going to wait. And we all know that when you start hitting external APIs, you do not know how long they will respond in. There has to be time windows for them to respond, but if you start maxing out your time windows just about each time, you're going to blow out your SLA before they blow out theirs. Because inevitably, you always end up being that person who has all of the APIs at one point or another. So time windows come in to be important. There's always more than one mode of failure. There is the failure case of it returned a failure. And there's the other failure case of it didn't return in time. Particularly when you're dealing with anything with users, machines, or otherwise, that time window is often as critical as the other kind of failure. But it's an indeterministic failure, but for your user, it's a failure nonetheless. And you can make this transactional. Joining, particularly on streams with certain tools, can actually be a transactional action. We can guarantee it happens once, we can guarantee it happens with isolation, and the join itself relies on the fact that the data is durable anyway. So let's talk about how to do it. Who here is familiar with Apache Flink? A few, so we'll talk a bit about it. So Kafka Streams is a part of the Kafka project. It works great. It has downsides. The downside mostly being is it puts load back on that same Kafka cluster you came from. So it says, would you like some Kafka with your Kafka, with your Kafka, with your Kafka, and down the well you go. Flink came from a slightly different school of thought. It's a robust real-time processing engine for batch and streams. It scales to almost any workload. Alibaba operate about 2 million cores of Flink to do all of their real-time processing if you've ever used their services, and they do that checkout deal thing they throw at you. That happens in real time through Flink. And the key thing here is has the usual cool APIs, has SQL, does that load of the ETL type things. Cool people like Decodable offer this as like a ETL as a service, and there's data enrichment and all the rest you could want. And it gives you this kind of monadic state on events. That is the one mention of monads I will make. I will try and stop. Yes, I was a Haskell developer once. So let's talk about Flink and complex event processing. So in kind of versions of this kind of approach, you just do a join. You'd have literally a join within a window, and you'd say, if all these events arrive, I can join them, I'll omit and filter that. But Flink has something called complex event processing, which gives you the ability to state that I need a sequence to happen in order, and also put time windows inside them. So you can say, if payment status starts initializing, and I then get an event that says completed within a time window, that is acceptable. But I can also then say, if it completed but outside the time window, this is not acceptable, but not a total failure. And you can now have this ability to chain these things together, because I need to add more guarantees. And we're now going down the well of adding more and more things, because the best thing about Flink and Kafka is everything's a stream. And inside Flink, which treats everything like a directly cyclical graph of processing, I can just add more and more of these processes together. And you don't really see services anymore, but just streams of data joined to other streams of data. But the best thing here is it's still independent to any of your business logic. You've basically now decoupled the success of events and the data of the events from the business logic workers you need to actually do this. So this does not rely on you changing your code in a big way. This can be added almost on top of almost any other process. And the key thing really here is that as you start diving into trying to add these kind of guarantees on existing systems, particularly, or even if you have a near greenfield approach, what you can start to say is, I need a Saga that defines this section of my code, these set of microservices. Let's say it's the user-defined flow. I need to onboard a user through these things, the email, the two-factor authentication, the token refresh, the access control stuff. Perfect, handled inside of Saga. But then from that Saga, on top of that, it's then set up payments, which relies on the first one, but has to be done separately. And these are now asynchronous things which can go back. And this is where we kind of go down the kind of Mandelbrot set of, it's the same thing repeating, but if you're familiar with the Mandelbrot maths, it's a very simple repeating sequence going into some slightly annoying fractals, but it's a very simple repeating sequence that creates this near infinite complexity, but you don't have to manage it. All we're saying to you as a user is say, define the 3 things that matter at this point in time, or the 6 things that matter, and accept and what are the consequences of the failure. And that's kind of the next piece on this. Because how do we roll back? We've talked about the ability to have isolated things. We've talked about durability, because everything in Kafka is on a written log somewhere. You can do multi-AZ writes. It's pretty straightforward. And how do we do a Saga in reverse? And this is where it gets a bit weird, because the number one thing you end up with is I have a series of actions taken. Some have succeeded, some have failed. But if you then just turn it upside down and read down the list again, you get a routing slip. So this is another one of those patterns from that wonderful book on design patterns. And routing slips basically say, these are the actions taken. Now, this is where I kind of break the domain-driven design rules quite heavily, which is that events are data, data is events, and there is no need not to have a large amount of metadata flying around. And by large, I mean an extra K max. Because if you think about how much data it takes to add an extra, block of JSON to the bottom, or hopefully Avro, if you're being sensible, please don't use protobuf. I will rant about that for 3 days later. Or any equivalent protocol, it doesn't really matter. If you haven't got enough network bandwidth to add the metadata to your event, that metadata has to live somewhere. And now your network calling it at will every time, rather than having it on hand when you need it. So this is where that kind of domain events versus domain data, I find, degrades, because the domain data needs to have enough metadata to be an event anyway. And the routing slip pattern basically says, this thing got to me, and it says, payment succeeded apart from this thing. So I now need to go to each of those services and undo them. And like statelessness, idempotency is an ideal. It's rarely a reality. And the critical point to make here is that if you've ever tried to do anything across multiple services, undoing them is next to impossible without having dedicated undo paths. There's a reason why we have puts, gets, deletes, and posts, and we don't use the post thing for deletes. Please do not use post as delete. If there's one thing you take away that. Delete is a different thing. And the ability to roll back a thing you've done often requires more actions than doing it in the first place, particularly when third parties might just be the person on the desk 3 points down or on the team to the left of you. Because you're outside of your domain space, you have to have dedicated ways to undo things anyway. There is no safe way, from anything I've seen, to enshrine that into a system by default. Even backing out a transaction on a ledger or on a bank is a non-trivial process. There's a reason they just say recredit, credit. They don't undo or remove the previous ones, because that deletes history. It means you lose your audit trail. It means if you go for a PCI DSS audit and you do that, someone's going to ask you some weird questions about why your log doesn't match your ledger. I wish I haven't seen that before. But as we all know, the weird stuff is basically the norm, and the happy path is that thing we dream about and tell people about in lectures. And this is the absolute criticality piece, which is the reason to use Kafka for this more than anything else is you have now got a history of anything. If your systems start blowing up and they resume, and that's great, they'll keep going. But when you start adding that lovely blue-green logic, so you put the next service next to it, you can set it to start last week, see if it flowed through, test on real data without ever disturbing what is live, right? And the reason for that to give you that kind of transactionality is because if you can be transactional on past data as well as future data, and it fails in the same way, you can also test that your code both handles happy, bad, strange, weird, and sadly normal events, which are all of the above combined, and still have some guarantees over what's really happening. And once again, idempotency is an ideal. I have worked on systems that claim to be exactly once and do vast cloud messaging. What that really turned into was multitudes of layers of checks through the network. The ability for us to have rollbacks across the 5 or 6 databases we used along the way. And quite frankly, was it 5,000 nodes of Redis along the way? Doing weird bits of Lua along the way to confirm things were really exactly once. And that's the problem is, anything which claims to be idempotent, claims to be all these things, is really just has made a compromise somewhere along the way. The compromise I'm suggesting in this kind of talk right now is that instead of saying your services must have all of their own logic to undo every action down the chain and push backwards, push that somewhere else. Put the logic that says the system has worked elsewhere. Put that into a stream. Put that somewhere durable. Put that somewhere with transactions on its own, and let the services live their own little lives and have the ability to act like true microservices. So, my inspirations. As I said, I'm trying to keep this short because it's until 9 a.m. So this is a talk. The one over there is about Kafka and brownfield systems by Anna McDonald from Kafka Summit last year. And this is Martin Kleppmann's turning your database inside out talk. Basically, these are just the QR codes. I will happily give links directly afterwards if necessary. But I figured QR codes was easier. The idea really here is so Anna talks a lot about doing this with Kafka Streams, very similar talk, but more about dealing with the true legacy systems, ones that just dump files everywhere. Martin talks really about the transactional side of Kafka, how it acts kind of like your database anyway, and kind of really double down that little point there is your database is a write-ahead log as well, right? If you start using outbox patterns, you're already using a write-ahead log, aka a Kafka-like type thing. If you just abstracted the write-ahead log and just used that, you effectively built Kafka. Now, the fact that it has all the other properties are why we love them. And don't get me wrong, you don't just use Kafka. And Kafka is not a database. Please repeat after me. Kafka is not a database. That is something I will always stand by. But it can do a lot of the similar things. And the trip of that record through the Kafka size and type network means that you do get guarantees as you go along. You can use those guarantees to guarantee other things, which is the important piece to get across. And as you start building out your kind of microservice network, which is on top of some level of service bus, and yes, Kafka, they'll say Kafka is not an enterprise service bus, but if it's doing the same job as one in the same way as one, it is one. And we don't need to be precious about naming things. A lot of these names came with connotations from yesteryear, which we may have a bitter experience of. Yes. I will never use Apache struts again. But that's because there are better options now. Please use Quarkus. And that's kind of my summary here is you can do this stuff across the networks. You can, if you use the right services and the right tools, get guarantees as you go through things. You can deal with the fact that anything can time out by having systems that respect time. You can unwind any piece along any way as long as you have the metadata of what you've done so far. And you can then codify into your microservices the ability to undo their last state or their last change. What this does is it means your microservices teams should not have to worry too much. They just have to respect the API, the schema of the topic they're reading from or publishing to. If you do evolve schemas, please make new topics. That is another plead from my perspective is schema revolution is a lie. You make a new topic each time, because then if you roll back in time, you roll back to the old topic, everything is clean. You never get that weird point where you've got to handle a schema revolution when you have to do a code rollback, because that doesn't really work. It really doesn't. For every client we have on Kafka right now, that has been a problem, even with all of the best intentions in the world and the Avro PMC chair working for us. So that is kind of where it ends. And so this is me to say thank you for listening, and please, any questions?
Your opinion about protobuf and Apache Kafka? You mentioned something.
Yes. So I have a personal bias against protobuf from bad experiences in the games world, where it was used as the actual wire format for UDP buffers. It was a very bad idea. It caused memory leaks on consoles. However, the reason mostly not to use protobuf in the Kafka world and the big data world is it isn't very well supported. Avro has the advantage of not being from Google and also having just been enshrined in that Hadoop big data kind of ecosystem for a very long time. All of the big data tools speak Avro. Most of them have a concept of protobuf, if not a first-class implementation. So it's just a matter of the happy path. If you use Avro, you're more likely to stay on the happy path with these tools. The actual capabilities, neither here nor there, to be blunt. They all work. It's really, your mileage may vary. Protobufs have the one advantage of more people seem to know gRPC, therefore no protobufs.
the weirdest defaults. What is your opinion on tuning the resiliency of the producers or consumers, the retries and the stuff?
So
Already had defaults.
So the defaults are the problem with the defaults in Kafka for exactly those circumstances is they vary per SDK. So if you use a librd Kafka one, particularly the Python one from Confluent, that doesn't default to. I think that defaults to axe1 rather than axe-all, versus the Java one I think defaults to axe-all. By default, there are two things to be very clear on. The first one is your topic settings are still going to override some of your producer and consumer settings. So your min in sync replicas is a really important thing to note. So if you have your brokers across multiple availability zones in a cloud or equivalent, you need to make sure your min in sync replicas is at least 2, because axe-all merely gets you to a number of acts of your minimum in sync replicas. It doesn't act every single broker. That's not how it works. So things like that are potentially traps. It's also the idea of saying, if I have 10 brokers and I have min-in-sync replicas 2, that's not really the point of having 10 brokers. You want it to be at least 4 or something, so you have the actual resiliency you need. So the trade-off, of course, is it's slower.
Play with the settings like producer buffer, producer retries.
Yes, you should, in most cases, be aware of them. Is my first response. These have changed in the past, the defaults. So just be aware of what they're actually at. Honestly, some of them have retry forever on them, which is terrible. I think that's the C# one had retry forever on it for a while as the default. But this is the problem. You need to make sure those defaults match not the defaults, the settings match what you need. Set the retries to a sensible number so you can then, not head of line block for the wrong reasons. I honestly can't remember the default settings now. I have a file that just overwrites them for most of mine. Any other questions? Sorry, I can't really see, so please shout out.